Hello and welcome. In this video, we're going to be sketching the function y equals x squared over 1 minus x squared. In the previous couple of videos, I've walked you through these 6 steps and how to use each step to gain information that's going to help you later on to sketch your function. And in this video, we're going to be applying all the knowledge that we knew in order to draw the function f of x equals x squared over 1 minus x squared. So this is our function. Let's put it over here. Let's start by doing the first step. We want to find the domain of the function. Okay, so first the domain. So over here, domain is basically the values of x that the function can take without violating or without having an undefined value. So what value of x over here that would make this whole function undefined? I know that if I have a rational function, if the denominator is 0, then the whole function cannot work. Am I correct? Then this is wrong. So let me find what value of x that will make the denominator 0. So I'll set my denominator to 0. I'll move the x to the other side, so 1 equals x squared. I'm going to square root both sides. Over here, I'm going to have x equals, what's square root of 1? It's 1. However, we cannot forget that it's plus or minus 1. So I have two values of x that will cause this to be undefined. The first is x equals 1. Second is x equals minus 1. So our domain is literally everything except x equals 1 and x equals minus 1. So this is our domains, all real numbers except these two values. And to write it in the correct, like the interval form, I can say that my domain is from negative infinity all the way up to negative 1, union with from negative 1 up to 1, then in union with from 1 up to infinity. This is my domain over here, so let's leave it at that. Let's take a look at the next step. We want to find the x and the y intercepts. So we can come over here and let's try to find the y intercept first. So I will set my x equal to 0. So f of x, or f of 0 now, is going to equal 0 squared instead of the x over 1 minus instead of x squared is going to be 0 squared. So this whole thing is going to be 0 over 1, which is equal to 0. So my y-intercept is at y equals 0 and x equals 0 and has a point 0, 0. So this is my y-intercept, a point 0 and 0. Let's check if we have any other x-intercepts, or basically solutions or zeros of the function. So to get the x-intercept, we need to put y as 0. So y is basically f of x. So 0 equals x squared over 1 minus x squared. So what I can do here is I can multiply both sides by 1 minus x squared. And then this is going to give me 0 equals x squared, square root of that, square root of that, so x equals 0. Again, my x-intercept is also at the point 0 and 0. So my x-intercept is at the point 0, 0. Now I finished the second step. Let's take a look and see what is the third step. So the third step says determine vertical asymptotes and holes. And zeros we already determined in this part, which is locating the x-intercept. So let's see how we can determine the vertical asymptotes or the holes. By the way, I did videos doing all these steps. It's very useful to go and find them. You will find the link to the full playlist on the top right hand corner. So holes and vertical asymptotes are basically x's that make the whole function undefined. So again, what values of x is going to make this function undefined? We established that x equals 1 and x equals minus 1. So this value could be a vertical asymptote or a hole. And the same for this value. Okay, to determine, I need to see is there any Is there any common factors for these x's that will cancel from your numerator or denominator? And if I wrote this as x squared and I factorized this part, this is a difference of two squares. So factorization looks like this: 1 plus x into 1 minus x. So this is one factor, this is the other factor. These are the denominator factors. Do I have any numerator factor that will cancel with them? In this case, no. So that is why these are considered vertical asymptotes. This is also a vertical asymptote. However, if I had, let's say that my function was, just for the sake of showing you, was having a numerator part of 1 plus x, okay? I will find after factorizing that 1 plus x will cancel with 1 plus x here. So this 1 plus x is associated with, because when 1 plus x equals 0, x equals minus 1. So this factor is associated with this x, which is minus 1. Since this factor is shared in the numerator and they're cancelled, okay, then this factor would now not be a vertical asymptote, it's going to be a whole, okay? And depends on the power of the numerator and the power of the denominator. I will show you lots of examples in the future videos, including wholes and vertical asymptotes, and you also have the previous videos where you can go and check in order to understand fully how to differentiate between vertical asymptotes and wholes, because this is very, very important. So in part 3, I said that I have two vertical asymptotes, okay? X equals 1 and x equals minus 1. So this is step 3 done. Let's do step 4, which is determining if I have a horizontal asymptote or an oblique asymptote. So let's come over here. Let's erase this. So for horizontal asymptotes, I always start by dividing every single term by the highest power in the denominator, by the x with the highest power in the denominator. So in the denominator, I have an x squared, which is the highest power of x. So I'll divide literally every single term by x squared. This is going to be x squared over x squared in the numerator, over 1 over x squared minus x squared over x squared. This is going to give me x squared divided x squared is 1 over x squared is basically 1 over x squared minus x squared over x squared is also 1. And I'm going to take the limit as x approaches infinity because I want to see my end behavior. So when x approaches infinity, this whole term is going to become 0 because 1 over a very large number is 0. And I will be left with 1 over minus 1, which is equal to minus 1. So y equals minus 1 is a horizontal asymptote. I don't have any oblique asymptotes over here, and I did a video on how to differentiate between horizontal, obliques, how to find oblique asymptotes, and so on. So over here I have my y equals minus 1. Let's actually write it. Horizontal asymptote is y equals minus 1. This is also like this. So for the fifth step, I need to find f dash of x and find the critical points and where f of x is increasing or decreasing. Okay, so my function was f of x. Okay, I will need to find f dash of x. So over here, to find f dash of x, I will need to differentiate this expression over here. And I know that this is differentiated by the quotient rule in differentiation. And it goes like this. F dash of x is going to equal the differentiation of the numerator, which is going to be 2x, times the denominator untouched. And then minus the numerator untouched, so x squared, multiplying the differentiation of the denominator. What is the differentiation of 1 minus x squared? Differentiation of 1 is 0, minus x squared is minus 2x. And then I will divide by the denominator power of 2. So simplifying this, 2x into 1, that's going to be 2x. 2x into minus x squared, that's minus 2x cubed, and then minus x squared times minus 2x, that is plus 2x cubed, over 1 minus x squared power 2. So this term and this term cancel, so I have my f dash of x as just 2x over 1 minus x squared to the power of 2. So this is my f dash of x over here. So let's see where are my stationary points, or where are my turning points. So to do that, I will need to equate my first derivative, or f dash of x, with 0. So 0 equals 2x over 1 minus x squared to the power of 2. So this means that 2x equals 0, which means that x equals 0. That's a critical point over here. I know that the slope at x equals 0 is going to be 0, and it's going to have a tangent horizontal line. So it's either like this or like this. So it's either a maximum or a minimum stationary point, and the next step is to differentiate, is it a maximum or is it a minimum. So to do so, we can test our points. So let's do, you can do a table, you can do a number line. Number line is easier, however I solve both ways. Let's put in all the critical points for this function. So we said that our domain is not including -1 and 1. So we have a point over here which is -1. We have our critical point which we calculated was x equals 0. And we have another point that is also interesting, which is point number 1. And I'm going to test f dash of x sign in every single interval of those. So over here, f dash of x is going to equal what? So let's take any random point over here and substitute it into f dash of x and see what is the sign of f dash of x. So if I say, let's say I'm going to take a point which is x equals -2. So this f dash of x is going to equal 2 into -2 over 1 minus -2 squared, all to the power of 2. And doing that, putting that in the calculator, it's going to give me a negative value. So the sign over here, I'm only interested in the sign, I don't care about the actual value. Negative sign over here. So this part from -infinity up to -1, I have a decreasing function. Let's take a value over here in this interval. So let's say x equals -0.5. That is between -1 and 0. So again, I'm going to substitute, instead of -2, x equal -0.5 minus 0.5. Substituting that's also going to give me a negative answer. So this part, the function is decreasing as well. Let's take x equals 0.5 over here and try to substitute. So this is going to be 0.5 times 0.5. This is going to give me a positive answer. It means that it's increasing over here. And then greater than 1, if I substitute 2 over into f dash of x, it's also going to give me a positive answer. So this part is also increasing. So now I have the intervals where my function is decreasing and increasing, and this can help me determine my turning point. Always before the turning point is going to be either decreasing or increasing, and after the turning point it's going to change. If it was decreasing, it's going to become increasing. If it was increasing, it's going to become decreasing. So over here, if the function was decreasing, meaning that it's having a negative slope, and then after this point it became increasing, meaning having a positive slope, that means that this point must be a minimum point. So now I have everything I need to know from my first derivative. I have the intervals where the function is increasing or decreasing, and I have everything I need to know, and I have my turning points location, and I have if they're a minimum or maximum. So now for the final step, we need to find f double dash of x. and to determine where the function is concave up and concave down, and if we have any inflection points. So part 6, we're gonna do something very similar to here. We're going to differentiate one more time. So if we want to find f double dash of x, that is going to equal, again, the differentiation of the numerator, which is going to be 2, into the denominator, which is 1 minus x squared to the power of 2, and the minus the numerator, which is 2x, into the differentiation of the denominator. What's the differentiation of 1 minus x squared to the power of 2? Differentiation of that, if y is this, then dy by dx, I'm going to use the chain rule. So this is going to be 2 into 1 minus x squared to the power of 2 minus 1, or to the power of 1. And then I'm going to multiply by the differentiation of what's inside, which is minus 2x. So this could be written as 2 into minus 2x is minus 4x into 1 minus x squared. So this is the differentiation. So this is going to be minus 4x into 1 minus x squared over here. And then I'm going to divide by the denominator, which is 1 minus x squared to the power of 2. However, I'm going to square it, so it's going to become to the power of 4. And let's simplify. Straight away, I can see that I have 1 minus x squared common. So let me take it out, and this is going to help me by cancelling one of 1 minus x squareds from the denominator. So this is going to equal, I'm going to take 1 minus x squared out. From the first term over here, I'm going to be left with 2 multiplying 1 minus x squared, because I just took 1 out. And then minus, I'm going to take this out, so I'm going to be left with minus 2x into minus 4x. Everything over 1 minus x squared to the power of 4. And then this whole thing is going to cancel with one of those. And this is going to be plus, this is plus. So this is going to equal 2 into 1 minus x squared plus 8x squared over 1 minus x squared to the power of 3. Simplifying, I'm going to have this as 2 minus 2x squared. Minus 2x squared plus 8x squared is basically plus 6x squared. So this is finally equal to 2 plus 6x squared over 1 minus x squared to the power of 3. So this over here is my f double dash of x. This is my second derivative over here. We can erase what we don't need. Save some space. Okay, so over here, I have my f double dash of x equals 2 plus 6x squared over 1 minus x squared cubed. So is there any value of x that will make my f double dash of x equal 0? Because when I equate my second derivative to 0, the x's I find are the possible inflection points. So over here, this is the same as 2 plus 6x squared equals 0. This is always positive. This is always positive. It's always going to give me a positive value. If this is 0, then my value is 2. So this will never happen. I will not have any value of x that will make my second derivative 0. So I do not have any inflection points over here. So the next thing is to determine the intervals where my graph is concave up and concave down. So we write all the critical points that we found. So we have a -1, we have a vertical asymptote over here, we have x equals 0, and we have x equals 1. We also have a vertical asymptote here, and this is a stationary point. And then we will test f double dash of x sign in every single interval. So let's take the same testing points. So let's say x equals -2. So this means that I'm gonna put -2 over here. So this is gonna be 2 plus 6 into -2 squared over 1 minus minus 2 squared to the power of 3. And doing this, this is going to give me a negative answer over here. So this part is going to be minus. So I know that this is concave down because f double dash of x is minus. Let's test the point over here. So let's say x equals negative 0.5 as well. If I put x equals negative 0.5, negative 0.5 over here, I'm gonna find a positive value. So here f double dash of x is positive, which means that this part is gonna be concave up. Let's test x equals 0.5. Again, 0.5 or negative 0.5 is the same because this is squared, this is squared, so it's gonna give the exact same answer. So f double dash of x over here is also positive, which means that this is a concave up. And over here, we take x equals 2. It's going to be the same exact answer as x equals minus 2 because this bracket is squared and this is also squared. So it's going to give the same answer if it's 2 or minus 2. So f double dash of x is going to be minus. So over here, we will have a concave down part of the graph. So if we copy all the information we have from the 6 steps, we can now successfully sketch our function. So if we come over here and we try to sketch our graph on the coordinates plane, let's start by looking at our domain. First thing in sketching, the first thing you should do is to sketch your asymptotes. So let's sketch the vertical asymptotes and the horizontal asymptotes. So we have two vertical asymptotes at x equals 1 and x equals minus 1. So let's say this is x equals 1, this is x equals minus 1. So let's sketch our vertical asymptotes in this way. So these are our vertical asymptotes. We have a horizontal asymptotes at x equals minus 1. So let's say this is minus 1 over here. Let's do. So let's say this is minus 1 over here. Let's sketch a horizontal asymptote in this way. So this is the asymptotes done. So this is x equals 1. This is minus 1. Over here, that is y equals minus 1. Okay. Let's now move on to sketching or putting any critical point or stationary point. So we know that we have a minimum point at x equals 0. When x equals 0 in the original function, when x equals 0, y is also gonna equal 0 because you're gonna add 0 here and 0 here. You're gonna find the point at 0 and 0. So the point x equals 0, y equals 0 is a critical point, and at the same time it's the y-intercept and the x-intercept. So what nature is this critical point? We figured out that this critical point is a minimum nature, so it looks something like this. So I know that the first part of this graph is going to be something like this. So I'm going to have a minimum point over here. So this part is going to look something like this. Okay, so this is the first part. Can draw it a little bit better. Yeah, so this part is like this. Okay, the next parts, I know that I will have something over here and something over here, something over here or over here. How do I know? First of all, I can see from the second derivative that from the interval from minus 1 all the way to the left, or from negative infinity to minus 1, I have a concave down shape. So it looks like this. So the graph cannot be this way because this is a concave up shape. So there is only one way for the graph, which is going to be this way. Okay, and the same thing from 1 up to infinity, I have a concave down graph. This part, if I drew this part like this, then it's gonna be a concave up graph, which is wrong. So I need to have a concave down, and I'm bounded by my asymptotes, so it must look something like this. Another way is also to test a point. Let's say at x equals 2, what is y? If I find the y over here, then it must be in this case, right? But over here, if you put in x equals 2, you will find the negative value of y, which is on this point. So it shows you that your graph should look something like this. I hope this video was helpful. Please stay tuned for the other videos. I'm going to be sketching lots and lots of functions. If you have a specific function in mind you would love me to go through all these points with in order to show you how to successfully sketch it, no worries, I can do so. Leave a comment down below. Don't forget to like, subscribe. Thank you so much for watching. Have a good day.